Okay, so we've seen the ideal gas equation. So that's PV equals nRT, and this assumes that your gases are behaving ideally, okay, according to the kinetic molecular theory that we introduced back at the beginning of the gases discussion. As you can probably imagine, not all gases behave in this ideal fashion. We're assuming that one of the assumptions here, according to the kinetic molecular theory, is that the molecules in the gas phase occupy negligible volume, meaning very close to zero. And another assumption from the kinetic molecular theory is that they do not exert any force on one another. There are no attractive or repulsive forces. Between the gas particles. Okay, however, under real circumstances, this is not necessarily true. What we actually find is that at some point, the volume that the gases occupy actually don't become negligible, meaning they can actually add up to a distinct volume. And then we also find that under certain circumstances that there are intermolecular forces of attraction that do exist between gas particles. So what are those conditions? Well, if we look, for example, at an ideal gas and the volume that it will occupy under STP conditions, we said that that's 22.41 liters. These other gases that are shown here, you can see they all don't fall on that 22.41 liter line. Some of them, a lot of them actually, chlorine, for instance, has a volume that is actually less than the molar volume, and so does something like ammonia, NH3. So why is that the case? Well, these are real gases, right? They actually deviate from ideal behavior under certain circumstances. And a couple of these circumstances are as follows. When we have high pressure, right? High pressure forces molecules to become closer and closer together, or the gas particles to become closer together. And as a result, their volume actually becomes appreciable, meaning not negligible, as the kinetic molecular theory suggests. We also find that at low temperatures, right, we slow down the molecules. We slow down the gas particles at low temperatures. And as they slow down, the gas particles can interact with each other more easily now. And as a result, there are going to be intermolecular forces that are going to become more significant. So when we deal with real gases, what we need to incorporate is some sort of a corrected term for both the pressure and the volume to account for these deviations from ideal behavior. So the corrected term here, the corrected terms include these parts to the van der Waals equation, which is what the new equation is going to be, that takes into account the increased pressure and also the intermolecular forces. So the volume, the extra volume that the gas themselves would occupy, and the increasing intermolecular forces that that they would have at lower temperatures. So these values, you'll notice that they have some terms A and N and B. Where do these actually come from? Well, we actually have a table of these that can be looked up, right? So we have different gases, they have different van der Waals constants for each of these terms. So for example, our A term here is listed in table 11.5 for a variety of gases, and then our B term over here is listed as well, right? The N there is a number of moles, B is your volume, same thing over here, N is number of moles, etc. So let's take a look at how we can apply this. So we have a sample of 3.5 moles of ammonia gas occupying 5.20 liters at 47 degrees. Calculate the pressure in ATM using the ideal gas equation and then using the van der Waals equation, right? So if we're using the ideal gas equation, P equals nRT. Okay, what are we given? We're given the moles here. This is our N, 3.50 moles. we have our volume B, 5.20 liters. We have our temperature T is 47. We want to convert that to Kelvin, so we add 273 to it. Actually, that gives 220 Kelvin. And then we're going to just substitute these into our equation. We want to find what do we need? Pressure, right? So pressure there would be nRT over V. So we substitute those in. Our N 3.50 moles. Our R 0.0821 liter atmosphere per mole Kelvin. And then our temperature there is 320 Kelvin divided by the volume, which was 0 liters. I know it may be tedious when you do these, but keep track of your units, write them down so you can see that they do cancel out. Moles go away, liters go away, Kelvin goes away. We end up with ATM as the only unit. That makes sense. We can find pressure. So using the ideal gas equation, it's 17.7 atmospheres. If I were to use the van der Waals equation now, but I can look up the terms, the constants for what gas do we have? Ammonia. So ammonia is NH3. So here it is, our term for A and our term for B are listed here, so we can substitute them back into our van der Waals equation. And then do the same thing. We solve for the corrected terms of the pressure, I'm sorry, for the volume at least, and we can determine the solution that way. So when we substitute those values into the van der Waals equation, we end up with the pressure being 16.2. If we compare that to the pressure, this is the real situation versus the ideal situation. Right, what we find is that the pressure under normal circumstances is less than that predicted by the ideal gas equation, and that's typically the case.